Hello, grade level statistics students. We're going to go over the quiz. This may or may not be the version that you have. There were two versions. You're watching this, so thank you very much. I appreciate it. Makes it worthwhile that I made it. Okay, so which of the two games would you rather play? Why? In your explanation, you must use math. So most of you figured out, in order to tell which one, I need to know the expected value. If I play game number one 1,000 times and average the outcomes, what will happen on average? Will it be a positive amount of money, a negative amount of money, or zero, or what? So you're multiplying these. So you have 10 times this. And if you know this already, great thing about the video is you can fast forward to whatever you need. So feel free. Okay, so I don't have these things worked out ahead of time, So you're going to watch me actually calculate it. Okay, so that is 4.4. And then game number two, we're doing the same thing. So I won't write it out, I'll just do it. 180 times 0.15 plus negative 70 times 0.4 plus 1 times 0.45. And that is this. So this is the expected value of game two. And you know what I'll do? I'll call that, what should I call it? Expected value of game two. I mean, why not? Equals this, and this is the expected value of game one. And once again, the meaning of that is if we play game two 1,000 times and take our overall winnings, or in this case it's probably losings, and divide it by 1,000, we would see that we had lost 55 cents on average every time we played. So over time, even if we gained some money in certain wins, in certain rounds of the game, we would overall lose money. So obviously we want to play game one instead, and you could write, I want to play game one because the expected value is higher, or something similar to that. Okay, so standard deviation. All right, now there's a way to use a calculator to do this, but I've been having you guys do this by hand. So I'll show you both in this video. So the long way, which you're not going to need in a minute, but it's good to know what's going on. The long way is to do 10 minus 4.4. And remember, 4.4 is the average, or the expected value, of this distribution. So we are taking each of these payouts and subtracting the expected value, the average. And we're squaring at that term, or that difference, and we're multiplying that by its probability. And that's going to be a term in a sum. So I'm going to do the same thing with this, times its probability, and that times its probability. And then I'll add it up, and I'll get what's called the variance. So that's, and I won't do this for every single, okay, so actually I'll do this an item at a time since I'm doing it all in the calculator here. So 12 minus 4.4 squared times 0.2. You can't see that, can you? Okay, well there it is. That's what I just did. Okay, so that's, okay, well now you can see. And then negative 50, have a good weekend, guys. That was the bell to end the pep rally there. Square that, get a positive, times 0.1. Okay, so this is the biggest term of the three for sure. So we add those up. And we get this, and that's the variance. And then we can get, if we do the square root of that, we get the actual standard deviation. Okay, so I'm going to show you how you can get that by using the, put a bracket there, by using the calculator as like a shortcut. And actually it was Maria showed me, I think it was Maria who showed me how this works. So if I go to Stat, and I go into Edit, and I'll clear these out of the way. I'll do Clear, Enter. That clears the list. So I highlight L2, clear, enter, that clears the list. So here, List 1, I'm going to put the payouts. Right, and next to them in list 2, I'm going to put the probabilities. Boom. Okay. Quit. Now I go back to stat, and I go to calculate one variable stats. Now if I just hit one variable stats, it gives me mean, standard deviation, and so forth of the set containing just these 3 numbers. So that's not what I was after. So what I want instead, I want one variable stats, and if I specify list 1 and list 2, it knows that what I want is I want to treat list 1 and 2 as the x's and probabilities of a random variable, of a probability distribution. Okay, so I get the 4.4 that we calculated here. I see that here as my mean, and I see my 18.5 right here as my standard deviation. And that little sigma is the standard deviation. Okay, and I don't know about the rest of that. We don't have to care about that. Okay, so anyway, that's just a shortcut, but it's, knowing how this happens by hand gives you an insight into what it actually is. Once the calculator spits it out for you, it's entirely possible to just forget what it even is and what it has to do with. But you can see, what we're seeing is the negative 50 is clearly producing the largest term, so that's the farthest away number out of the 3 from the center. Okay. Alrighty then. So given x and y, we've got their means and standard deviations. What are these means and standard deviations? So we'll say mean and standard deviation. In each case, what is it? Now, we're adding 3 instances of x, and we can simply add means. And I mean, I feel silly writing it 3 times, because obviously I could have just done 140 times 3, but that's what it is. And believe it or not, this one is the same. If I do 3x, that would just be the same thing. It'd be 140 times 3, and I would again get 420. And x minus y is pretty simple as well. I just do 140 minus negative 22, and I would get this. And remember, I'm subtracting a negative number. That's why I get 162. Standard deviations, though, these are not going to be the same. And that was a point that we made in class. Here with 3x, I can simply, well, actually, let's do it this way. We'll start with this. Remember that I can add means together. 140 plus 140 plus 140. Just like that. However, I cannot add 24, 24, 24 and call that the standard deviation, because standard deviations don't add like that. But variances do. So I can say, well, what's the variance of these things? And I can say, well, the variance is the square of the standard deviation. So I can do 24 squared and 10 squared, and I get 576 and 100, right? And then those add together. So if I do x plus x plus x, that's 576 plus 576 plus 576, or just times 3, of course. So that's 1728. So the standard deviation of x plus x plus x is going to be the square root of the variance, just like standard deviation is always square root of the variance. So I can just do the square root of and get 41.57. So that's what this is. Okay, now this is different. Here, I can just, well, I can multiply, let's see, I can take the standard deviation and simply multiply it by 3. And it's actually that simple. The textbook makes it a little more complicated, and I can't remember why, but we don't need, certainly for this example, we don't need it to be any more complicated than that. So we're multiplying the random variable by 3.
High school students, the buses are leaving in 3 minutes and 47 seconds. If you're riding a bus and that is your transportation home, you have 3 minutes and 46 seconds now to get to the bus circle and get on your bus. That means all members of the Fighting Tiger Band need to move it to the bus circle so you do not miss your bus.
Okay, so that announcement is now over. Okay, so we have x minus y. Okay, so x minus y, we subtracted them. Now, question, what do you think we would do with this? Most people would think, well, just like with adding these, we added the variances, just like so. Here, maybe we just do variance minus variance. Well, that would start to make sense, but you can find out by reading the book that even for x minus y, we would add the variances. In other words, for the variable x minus y or for the variable x plus y, either way, we're talking about this plus this. So we have 676, and we have the square root of that. So the variance of x minus y is 676, standard deviation 26. Okay, almost there. One more thing, this bonus. Now, a student actually came up with this idea last year, and I thought it was one of the funniest things I've ever heard. The idea that there could be a casino game where it has an overall positive expected value, but it's almost a guarantee that you'll come out ahead. Or let's put it this way, it's very unlikely that you'll have to suffer this consequence. So you could potentially lose $1 billion by playing one round of this game, right? But if we make it unlikely enough, then maybe people will be willing to pay, willing to play. Okay, so negative 1 billion. So some people just put a 0 here and said that this was a 25% chance. Now, I didn't say you couldn't do that, so I had to accept it. But I wasn't expecting people to do that. I thought people were going to say, and some people did, that the negative 1 billion would just have a very low probability. And you can make it, I can't remember what the threshold was, but you can set it up with algebra and figure it out, and I think Zach did. But you can set this up and say, all right, really, really low probability, and then just make sure that the 3 probabilities add up to 1. And so you could say 0.75 plus 0.000000001, and then say 1 minus that. And you would have 0.24 with all those 9s. So that's like 8 9s. So it's ridiculous. This whole thing is ridiculous because look, I've got 25 minus 0.75. If I want to do expected value now, I have that product. The next term, the product is 0, of course. And then here, actually, let's calculate that. So we have negative 1 billion times 0.000000001 is negative 0.1, exactly. And the other one, the other term is 25 times 0.75. So you add those together, look at this. If you keep playing this game, you will win, on average, $18.65. But actually, it's extremely unlikely you'll ever lose money. I mean, you know, you'd have to play this game a lot of times for that to be an expectation to ever happen. So really, this is almost just like totally like an ATM that's like bottomless. You get 3/4 chance of $25. You can just show up whenever you need, pull the lever, out comes $25. You just keep going back as many times as you want. This just only thing is, every once in a while, there's somebody who gets stuck with this enormous bill. All right, so thanks for watching, guys. See you later.